All right, let's take a look at our lesson for today. So today we're going to continue with our topic of U substitution, but now we're going to bring definite integration into it. There's a little bit of a difference. So let me remind us when we go back to our U sub, what were we doing? Remember, we are looking for this kind of format where we have a composite function and we have one of them inside of the other one and its derivative exists. Okay, so that's kind of what we're looking for to use U substitution. So keep in mind that if the integrand, or the integrand is this part right here, isn't a formula that you know, then it's probably U substitution. That's what it probably is. And we practiced that last class period. So let's bring definite integration into it. So we're still looking for this kind of scenario right here. We're still looking for that, okay, where we have a composite function where we have g of x is inside of f of x and the derivative of g of x is there. It exists there. And so what we want to do is, let's kind of keep in mind that this variable and this variable and these bounds are all related. They all belong to x. Okay, so there's x's inside of these functions. This is a dx, and these are x bounds. That's a really important concept for us to understand. When we move into U, we have to change. Okay, let me say it differently. So one technique is to change the bounds to U bounds, and that's what we're going to be doing pretty much most of the time, because that is a really important skill for us to have. Now, is that the only way to do it? No. And as we work through it, I'll talk to you about the other way to do this besides changing the bounds. But changing the bounds is the technique that we're going to use. All right, so, all right. So let's look at this. Here's our first example. So I've seen they do multiple choice questions like this on the AP test. They tell you what the U is, and then they ask you what would the bounds be. Or they might tell you what the U is, and they would ask you which integral is equivalent. They like to do things like that, which is why we're learning the technique where we change the bounds. So let's kind of start our U substitution work. They're telling us U is 2x plus 1. So U is x squared. U is x squared plus 1. And they're asking us, they're not really asking us to do this integration. What they're asking us to do is, what would the U bounds be? Okay, so what would they be? I'm actually going to write it over here. This part right here, this would be U. And so we would have like U cubed. Okay, and then our du would be 2x dx, so 1/2 du equals x dx. Then we'd have our 1/2 here and our du there, and then this part right here, the x dx turned into half du. Okay, so that's like we would do last time. Notice that I haven't copied over the bounds. If I put a 0 and a 1 here, that would be incorrect because those are x bounds. Those are not U bounds. So how in the world do we find U bounds? Okay, so what we do is we take this expression that we have used to talk about the relationship between U and x. We take that original expression and we use it to transform our x bounds into U bounds. So I'm going to write U for lower. That's the lower bounds would be, let's see, so U would be 0 squared plus 1 or 1. So my lower bound is actually 1. And what did I do? I basically took this relationship and I used it to change the bounds. That's how we change the bound, is we take the U and X relationship and we use it. So now my U for my upper bound So u would be what, that was a 1, so 1 squared plus 1, and that would be 2. And that would be my u bounds. Now, they didn't ask us to go ahead and, actually work it out, but that's what we would have. Okay, so I want to pause here for a second. Is everybody okay with changing the bounds? We're switching from x bounds to u bounds. We should write that down. We are changing from x bounds to u bounds. That's our whole purpose right here. Okay, so that all of these, this is u bounds, this is u, and this is u. All of that is u. We started with, all of these things were x. That was x bounds, that was x, and that was x. We're doing a complete, basically we're transforming the complete thing, not just part of it. So I will tell you the most common mistake that I see when working with u substitution with definite integrals is forgetting to change the bounds. That is like the most common mistake that I see. Forgetting to change the bounds. Please don't forget to change the bounds. Just, I actually do it all at once. I do all of this thing all at once so that I don't forget. I do it at the same time. Once I get my u and my du, I go ahead and I get the bounds immediately. Otherwise, I'm afraid I might forget. Okay, so let us move to some examples that we can work. I think I've got a couple of them. Okay, so let's think about the locations where u normally is. So as we're looking at this integrand, what would we think u was? X cubed plus 1, that's what it is. So we're going to write that out to you. So u is x cubed plus 1. Would it help to continue to highlight the parts, how they match, or are we okay? Would the highlighting help or no? Are we good? Okay, so that's what u is. So du is 3x squared dx. I don't have a 3 to pull out, so I immediately move it over. 1/3 du equals x squared dx. Now, since it's a definite integral, I'm going to immediately go into my bounds. I'm going to change my bounds right now. I can either keep it a list like this, which is fine. So my lower bound, I'm going to abbreviate L for lower bound. I would have, what that would be, 0 cubed plus 1, which is 1. My upper bound, again, this is my scratch work. I won't be grading your work, but it's important to show what you're doing. My upper bound would be, what, 2 cubed plus 1, so that would be 9. So this is all of my u sub work. Okay, are we all okay? So now so right now this is x bound, these are x's, and that's dx. I'm going to basically transform the whole thing to be u bounds, u's, and du, all of it. So my bounds I discovered would be 1 to 9. I've got the 1/3 out here. That's from here, right? There's my 1/3 du. And then I have u, basically the square root of u du. Okay, so I just switched all of my bounds to u's, and all of my stuff is now we're in u. And I'm not going to go back. I'm not going to go back. Okay, I'm going to stay, because that's way easier to work with than what we had. Okay, so let's work through that. So this is really, that's u to the 1/2, right? That's what that is. So I do my reversal power rule. I add 1 to 1/2. So 2/2 plus 1/2 is 3/2. Okay, I got my 1/3 out there. So 3/2 dividing by 3/2 is the same thing as multiplying by 2/3. U to the 3/2. I'm evaluating it from 1 to 9. Okay, are we okay? Okay. So let's look at our, let's see, 1/3 times 2/3 is 2/9. And then I have 9 to the 3/2. I'm just going to do it like this so that I like to multiply by the fraction after I do all the other stuff. So I'm just going to pull that out to the front. So I plug in a 9 and then minus 1 to the 3/2. And yes, this is something that we are expected to do. We are expected to know how to do 9 to the 3/2. So let's think back to our previous work with exponents. Remember this, the bottom one is the type of root, and the top number is the power. Right, so I would square root 9. The square root of 9 is 3, and 3 cubed is 27. So I've got 27 minus, and 1 to pretty much anything is 1. I just love 1. It's great. Okay, so we've got what? We've got, now these numbers are really big, which is troubling to me. So this is what I would do. You certainly do not have to do what I'm getting ready to do. I would split it out like that so I could reduce this fraction. That 27 is really big for me. Y'all are probably like, oh, that's a small number, but for me, that's big. So let's see, 9 goes into 27, what, 3 times? So actually we're in ninths. Let's just do that. So yeah, we've got to do that anyway. And in fact, what I was going to do, I was going to bring this down to 6, but then I have to move it back to 9, so it really doesn't matter. So we can just leave it. Why don't we just distribute? So this is 2/9 times 26. And yes, that is what? That is 52/9. And there really isn't much reducing we can do there. Sure. How are we doing with our very first definite U sub? Do we have any questions? Are we okay? Yes? Okay, I'm taking it. We're okay. Okay, does anyone still need this? Okay, we have one more like this. So let's go to our next one. So here we go. So let's think about our rules that, well, at least the patterns I talked about. What do you think U would be in this particular integral? It's probably sine. Yep. So U would be sine x. That means du would be cosine x dx. I want to immediately change my bounds. Otherwise, I'm afraid that I might forget. So my lower bound would be sine of 0. Oh, look at those unit circle values. Sine of 0 is, 0, right? And then my upper bound would be sine of pi over 2, and that is 1. Right, this is all my work for getting rid of U, or going into U and getting rid of the x's. Okay, are we okay with that? All right, so let's change our bounds. Our bounds are now from 0 to 1. And cosine is gone because this part right here, cosine x dx, turned into just du. So I've got u, the square root of u du. That's what I got. Which looks way easier to integrate, right? Don't y'all agree? That's way easier to integrate than what we had. So I'm going to just put a little note out here. That's the same thing as u to the 1/2. So we're going to do our reversal power rule. So 1/2 plus 2/2 is 3/2. And I'm dividing by 3/2, which is the same thing as multiplying by 2/3. And I'm going to do this from 0 to 1. Okay? So I'll keep the 2/3 out like I did before, or whatever the fraction is, doesn't matter. So I have 1 to the 3/2 minus 0 to the 3/2. And 1 is delightful, isn't it? 1 to the 3/2 or 2/3 doesn't matter. It's still just 1. What do you think 0 to the 3/2 is? is 0. So we basically have 2/3 times 1, or simply 2/3. Now before we go on, we have one more topic here. Before we go on to that, I want to talk to you about the other way we could do it. And this might be like, oh my gosh, please don't tell me another way. And if you don't want to listen, please don't. But you need to understand there is another way to do it. And some students prefer this way, but doing it this way can get you mixed up. So what other way do you have to do it? Okay, so what I'm going to do is I'm going to take this right here, and I'm going to move it over here, and I'm going to do the other way in pink, okay? So what we would do is, if you didn't want to change the bounds, you could stay, once you've done your antiderivative with the u, you could, remember how we do it with the indefinite integral, how we put the u back in? Remember that? Yeah, you could put the u back in. You could do that. You could say, oh, this is 2/3, and u was sine x raised to the 3/2, and then you would evaluate it with the x bounds, which is 0 to pi over 2. And you could totally do it that way, and you're going to get the same answer. But the danger is, I'm just going to be perfectly honest with you, the danger is when you go back and forth between these techniques, because you will have to do this way. Okay, sometimes we get muddled up and forget to change our bounds. So I'm just going to say this is, we'll call this method 2. And we would need to proceed with caution if we're going to go back. We would proceed with caution because, you know, we don't want to get our bounds confused. But you're going to get the same answer either way. It doesn't matter. Okay, so I'm going to pause here for a second. So this is u substitution with definite integrals. How are we doing? Everybody okay? Okay, I have one more topic that we're going to talk about. And it's called algebraic substitution. And so there will be times where we're doing a u substitution and we have extra x's left over. So after we find a u substitution, what if we have extra x's that are not taken care of by the derivative, the du or the derivative? What do? We do, it's called algebraic substitution. And I'm going to take you through this particular problem just to demonstrate algebraic substitution. Okay? All right, so let's focus on this problem. As we look at this, what do we think u is going to be? X plus 1. U is definitely x plus 1. So let's write that out. So u is x plus 1, du is dx. So we've got this part turned into u, and this part turned into du. I'll just put little notes by it. This is going to be a u, and that's going to be a du. Is there something that we haven't dealt with? Yeah, the x. We haven't dealt with the x. This is the type of problem I'm talking about that's called algebraic substitution. So we are not allowed to change part of the integral and not all of it. So what do? Well, what we do is we take, this is our original substitution right here. We take it and we solve it for x. So x is going to be u minus 1. Okay, and I am going to take that and replace it right there. I'm going to put it right there. So I've got the integral of that x turned into u minus 1, and I've got the square root of u du. I'm going to pause here for a second. Okay, are we okay? So in integrating that, we know we don't have quotient rule with integrals. It's not a thing, so I'm going to need to rewrite it. Any ideas on how I should rewrite it? Yep, absolutely. We need to, we can either bring this up as u to the 1/2 and distribute it, or we can make two different fractions out of it. Either way, it's going to work the same way. All right, so let's rewrite it. So I have u over the square root of u minus 1 over the square root of u du. This first fraction I can simplify, right? That's u to the first over u to the 1/2, which would leave me what? If I have u to the first over u to the 1/2, what does that simplify to be? U to the 1/2. This is u to the 1/2, and that is, I'm just going to rewrite it in exponential form. That's u to the negative 1/2. Okay? Uh-huh. Oh, I'm glad you asked that. So if it's 1 over, it can only be 1 over the single variable to the first power to turn into natural log. It can't have a squared on it or a square root. It can't have anything on it to turn into natural log. Just 1 over u or 1 over x turns into natural log. That's a good question because I see that a lot. Okay, good question. Anything else? Okay, so let's do our reversal power rule. So I add 1 to 1/2 and I get 3/2. So 2/3 u to the 3/2 minus, I add 1 to a negative 1/2 and I get 1/2. Divide by 1/2 is multiplying by 2. Okay, that's 1/2. Am I done? Am I done? No. What do I have to do? Yep, I got to put the u back in. I have to put the u back in. Now, I can't combine u to the 3/2 and u to the 1/2 because they're different exponents, but I can put the u back in. So the u was, what, x plus 1. So I have 2/3 x plus 1 to the 3/2 minus 2 x plus 1 to the 1/2 plus c. And if you would rather write it as an radical, you certainly could. I wouldn't require it, but if you wanted to, you could. And there we go. That's algebraic substitution. So just to recap, the important topics that we're talking about here, for u substitution with a definite integral, the important thing we talked about is making sure to change the bounds. Okay? If we have an extra x left over, we talked about something called algebraic substitution, and we need to make sure to take care and turn everything to u's. How do you know which columns put in plus c? Good question. The plus c's go with this kind of integral, the indefinite integral. So if we just have no bounds on it, this is called indefinite, and these need a plus c. The definite integrals with the bounds on it, I'll just make up some bounds like 1 to 3. This is definite, is no plus c, because we have to do our fundamental theorem, f of b minus f of a. Okay, so that's how we know if we need a plus c. Any other questions?